Welcome to S Chemistry. This is I'm your instructor, Dr. Suhas Gauri. I will be teaching BSc 5th semester Physical Chemistry course on Elementary Quantum Mechanics. Here is the outline. So first I will take Hermitian Operator Schrodinger wave equation and its importance. So let's see who is Schrodinger. So Edward Schrodinger was one scientist. In 1926, he gave wave equation to describe behavior of electron wave in an atom and molecules. Like each atom and molecules, there always be one electron, and how electron behave into the atom and molecules under the certain conditions that we can plot into the wave equation. So in Schrodinger wave model of an atom, discrete energy levels or orbit proposed by Bohr are replaced by mathematical function psi. So that are which is related to the probability of finding electrons at various places around the nucleus. So that mathematical function, that psi, it will always give the probability, not anything else. So only the probability will give like how much time electron will stay at particular position or particular space into the nucleus. Now we will see simple equation of sinusoidal equation, that is for a wave model. So now matter wave can be expressed on the basis of an equation called sinusoidal equation for a wave sinusoidal equation, that may be expressed as follows. So here y, that is y equal to a sine 2 pi nu t, where y is the displacement during the propagation of wave, a is the amplitude of the wave, nu is the vibrational frequency, and t equal to time. So y is always showing the about the amplitude or uh, of the wave. So here you can replace 2 pi nu, that is equal to pi, and omega, that is a angular velocity, uh, where omega equal to 2 pi nu. If you replace this nu with some, where as x equal to ct, so where x is the distance covered by particle in time t and c is its speed. So you can write this equation into the where y equal to a sine 2 pi nu x by t. So here they have replaced only parameter t. So instead of t, they have replaced t with x divided by c. Now, what happen if you replace with a wavelength parameter? So instead of frequency, we can write this equation where we can. So this equation is known as c equal to nu lambda. So lambda here is the wavelength of the wave. So where this equation can become y equal to a sine 2 pi x by lambda. So these are the various forms of the same equations. So now your x can be replaced with a psi function, that is wave function. So the wave function psi for a such wave may be written as psi equal to a sine 2 pi x by lambda. So, so now consider the simple wave motion as that of the vibration of a straight string. Let y be the amplitude of this vibration at any point. Wave coordinate is x at time t. So let y be the vertical displacement during the propagation of wave at any point. Wave coordinates is x at time t. So it's always giving position with respect to time of a particle. So the equation of quantum mechanics was derived by Edward Schrodinger. So the equation of such wave motion may be expressed as del square psi divided by del xx square equal to 1 by c square into del square psi by del t square. So this will become equation number 1. So this equation is given by Edward Schrodinger. Uh, so Schrodinger, taking into consideration the basic equation of standing wave. Uh, so how this equation for the standing wave. So where c is the velocity with which the wave is propagating. Psi, the wave function here is the function of space and time, and may be expressed as like this. So psi, you can write psi equal to function of space and time. So we are from space here space is your one dimension. That's why only x is coming over here, and you can make two different equation like psi equal to fx, the function of x only, and function of time gt, that is function of time only. So this will become equation number 2. So for stationary wave such as occur in a straight string, the function gt be represented by the expression where gt, you can write this function of a function of a time, that is equal to a sine 2 pi nu t. So this will become equation number 3. Now that equation can be written as psi function can be written as psi equal to fx into, instead of gt they have replaced gt term over here with a sinusoidal wave equation, that is a sine 2 pi nu t. So this will become equation number 4. So hence if you differentiate with respect to double differentiate with respect to time, so you will get this equation of a psi, that is equal to fx 4 pi square mu square a sine 2 pi nu t. So this will become equation number 5. So now instead of this is fx and this is your gt term, so you can uh, get together over here, and the constant whatever the 4 pi square nu square, this will be the always constant, so you can take it outside. So this will become equation number 6. So if you double differentiate with respect to time, so finally you will get fx into gt is nothing but your psi function. That's why you can write as a directly psi. So similarly, it follows from equation number 4 that del square psi divided by del x square, that is equal to del square phi fx divided by del x square into gt. So this will become equation number 7. So combining equation 1, 6 and 7, finally we'll get the del square fx divided by del x square, that is always equal to minus 4 pi square mu square by c square into fx. So this will become equation number 8. So equation 1 and 8 are the time dependent. So in terms of lambda, that is wavelength, this is c equal to mu lambda. So 1 by lambda, that is if you rewrite this equation in terms of 1 by lambda, you will get the c by mu. So if you take square root square on both sides, you will get 1 by lambda square equal to c square divided by mu square. So if you put this into the equation number 8, you will get equation number 9, that is del square fx by divided by del x square equal to 4 pi square divided by lambda square into fx. Now that equation number 9 you can rewrite in terms of momentum uh, or Planck constant, that is del square fx divided by del x square equal to minus 4 pi ms square v square nu square divided by h square into fx. So this will become equation number 10. So as the energy of electron may be considered as the sum of its energy and potential energy, so E equal to your T plus V. Here T is nothing but your kinetic energy and V is your potential energy. So if you combine together, you will get the total energy. So now here we have to calculate the kinetic energy, because once you know the particle velocity and mass, you can calculate the uh, kinetic energy. So T equal to E minus V. So here T or kinetic energy, that is equal to half mv square. So multiply numerator and denominator of above equation, like t equal to m square v square divided by 2m. So you will get finally m square v square equal to 2m t. So m square v square equal to 2 m in bracket. Instead of t, you have to write this equation e minus v. So if you write 2m in bracket e minus t, that is equation number 11. So substituting the value of m square v square from equation 11 in equation 10. So del square fx divided by del x square equal to minus 4 pi square into 2m in bracket e minus t into fx divided by x square. So del square fx divided by del x square equal to minus 8 pi square m in bracket e minus t fx divided by h square, that is equation number 12. So this is a time dependent Schrodinger equation for a single particle of a mass m moving in one direction only. So considering the motion of microparticle in three dimension, this equation has been modified as where fx is a function of x only, that is will become a psi x function, or in for three dimensional your function will be the x, y and z. So three parameter will be there. So corresponding in psi function also you will have three different parameter x, y and z. So here equation number 12 is a time independent Schrodinger equation. This is very important equation uh, in quantum mechanics. So generally chemistry people always will follow the Schrodinger wave equation, and physics people will always follow other quantum mechanics that will come to later. So far, we have seen time-independent Schrodinger wave equation in one dimension. Now we are going to see how it will see in three dimension. So here is the equation number 13. So del square psi divided by del x square plus del square psi divided by del y square plus del square psi divided by del z square, this is equal to minus 8 pi square m in bracket e minus v psi into psi, so divided by h square. So this is in three dimensional Schrodinger wave equation. Now left hand side is minus, so if you take in right hand side it will become plus, and this if you could uh, take out psi as a common, then you will get this differential equation. So here this differential term we denote as a uh, nebula, that is a Laplacian operator. We also call it a nebula symbol. So this is a differential operator. So this is nothing but a double differential operator. So del square divided by del x square plus del square divided by del y square plus del square divided by del z square. So this we call it a Laplacian operator. So equation 13 is a well-known Schrodinger wave equation proposed by him in 19. It is also written in the form of following forms, uh, like in bracket minus h cross square divided by 2m in bracket del square by del x square plus del square divided by del y square plus del square divided by del z square, bracket close, plus this v is potential energy, so big bracket close, into psi equal to e psi equal to E side. So here equation number 14 comes due to like the here in equation number 13 they have replaced h h instead of h, they have replaced h cross. So h cross is nothing but h by 2m. So this equation you can write in other form also in terms of symbolic. Here this is a Laplacian operator. Double differentiate is nothing but your Laplacian operator, that is minus h cross square divided by 2m into Laplacian square plus v So this whole term we consider as a Hamiltonian into psi equal to E psi. So this equation number 15. So defining the Hamiltonian operator H cap as a minus Hs cross square divided by 2m into Laplacian operator square plus V. So then equation 15 becomes H psi equal to E psi. So this is given by Edward Schrodinger, and for this he shared in 1933 Physics Nobel Prize with the British physicist P.A.M. Orac for the discovery of new productive forms of atomic theory. Now we are going to see the physical interpretation of wave function, which is given by Schrodinger, and its importance of Schrodinger equations. So the Schrodinger equation can have several solutions, not all of which corresponds to any physical or chemical reality. Such solution or wave function are therefore not acceptable. So we have some four types of conditions for the acceptable wave function. So they should follow the following conditions. The wave function psi is a single valued, that is, for each value of a variable like x, y, and z, there if only one value of psi. Suppose one of the variable is an angle theta, then single valued denotes of psi requires psi theta equal to psi theta plus 2n pi, where n can be any integer. Second condition is the wave function psi and its first derivative with respect to its variable must be continuous. That is, there must not be any sudden change in psi when its variable are changed. Third condition is an acceptable wave function as it is single valued, finite, and continuous function. So it should be always single valued and finite and continuous function. And fourth condition is for a bound state. So for bound state, psi must vanish at infinity, because uh, after boundary there is no probability of finding any electron into the wave function. So therefore, the psi function should vanish at infinity. So less than infinity, only some probability will be there. So you will get that time a solution. So if psi is an complex function, then psi star into psi must vanish at infinity. So psi star is the complex conjugate of psi. So satisfying the above condition, the Schrodinger equation yields significant solution for certain definite value of the total energy E. These values are called eigenvalues. So equation H psi equal to E psi is thus an eigenvalue equation, and we can write it as H cap psi n equal to E n psi n. So in bracket n equal to 1, 2, 3 and so on. So where n is the quantum number. We express equation 1 by saying that psi n is an eigen function and En are the eigenvalues for an atom. So E is nothing but your energy terms. So that's why we say it's eigenvalue. So each eigenfunction has eigenvalue, corresponds to eigenvalue. So these eigenvalues corresponds to discrete set of energy values postulated by Bohr. So the fifth point is the eigenfunction are said to be form of an orthonormal set, that is integration of psi n star into psi m dt. This has to be equal to either 0 or 1. Uh, when it will be 0 when n is not equal to m. So this is your n and this is your m. These two values are not same, then you will get the 0 value, otherwise you will get the value 1. So we call it when n is equal to m, you will get 1 value. That time we are said to this function, this sin function are the orthonormal set to each other. So this value we call it delta nm, and this delta nm is nothing but your called Cornell delta. That is, they are orthogonal when delta integration of psi n star into psi n dt equal to 0, and normalized when psi integrated psi n star into psi n dt equal to 1. What is the significance of wave function that we are going to see over here? The wave function psi is in a Schrodinger equation by itself has no physical significance, except that it represents the amplitude of the electron wave. So, however, the square of wave function y is psi square gives the probability of finding an electron of a given energy E from place to place in a given region around the nucleus. Third is significance is the intensity of the light is proportional to the square of the amplitude of the light wave at the point. So if you want to know the intensity of the light, that is always will be proportional to the square of the amplitude of the light wave. So the fourth point is similarly the probability of finding an particle at particular point that will be always proportional to the square of the wave function at that point. So this wave function is nothing but your finding the probability at particular point. So you can tell using the any wave function where the what is the, how much probability is there to find in a particular place. So it is also possible to identify the regions of the space around the nucleus where is a high probability of locating an electron associated with a specific this space is called an atomic orbital. So we can say definitely we are going to find the electron around the nucleus, that is a very high probability to locate any electron into the specific space, that is an we call it atomic orbital. And atomic orbital thus represent a definite region in three-dimensional space around the nucleus where high probability of finding an electron of a specific energy E. So there will be always high probability of finding electron of a particular specific energy E. Thank you. See you in next lecture. Till then, happy learning.